All right, greetings everyone. Welcome to today's talk, Malware Techniques. My name is Rad, and I'm really excited that you guys have been able to take some time out to come and view this talk. So, without further ado, let's get started. So, I'd first like to open this talk with a statement. Knowledge should be free, and I don't think that needs much explanation. But I think that's an important thing to keep in mind once you start learning new things and almost keeping that knowledge to yourself. I think that's not a great thing to do. So without that political agenda, let's move on to the next slide. I think credit must be given to a couple people. Most importantly, Jonas. Jonas has been helping me a lot throughout the past year and more, and a lot of these techniques wouldn't be possible without his help. So I've just got to give a special shout out to him. Peter Wynne Smith and Modix have done some awesome work behind some of these techniques in Nighthawk, and Spider's also done some of the work and the inspiration for some of these techniques. So with the credits aside, let's move on to today's agenda, and I'm not going to go through who am I, because frankly you don't care who am I, and I don't care who I am. So let's get started with our first topic for today, which is vectored exception handling. So how many of you have heard of vectored exception handling before? Maybe some of you haven't. So what exactly is it? So at a high level, an application can register a handler. This handler will get called whenever an exception occurs, which is kind of the main difference with structured exception handling, is it's not frame-based. So in your program, whenever an exception occurs, we can register a handler. EDRs may register handlers as well, and this will call these registered exception handlers. Internally, these exception handlers are stored as a linked list, and we'll kind of dive in a bit more into that later. So it's also possible to remove and add exception handlers with the Win32 API. So we can just call add vectored exception handler or remove vectored exception handler. If you want more information on what exception handling is, definitely go check out MSDN, as it's a good source. Also, you can find a lot of this information from reversing. So whenever an exception does occur, the handler that's been registered receives a structure containing information about the exception. This structure contains the exception information, a capture of the context, so all the registers, the value of the instruction pointer and more. And we'll kind of dive into this later on. So to kind of actually understand what exception handlers are for people who haven't heard or used them before, we'll just go for a simple example where we register an exception handler, create a fake exception, or a real exception in this case, and then recover from this exception and remove the exception handler. So if we look at the main entry point of our function, we call add vectored exception handler, and the first parameter can be either 0 or a positive integer. If it's 0, it gets, as I mentioned before, the exception handlers are implemented internally as a linked list. If we specify 0, it's appended to the tail, or inserted to the tail at the tail, and if it's 1 or any other positive integer, it's inserted at the head. And the second parameter is pointed to, or the address of our exception handler, which in this case is dummy exception handler, and this exception handler receives a pointer to exception pointers, and this essentially is a bunch of exception information. So when an exception does occur, we receive this information. So going back to the main function, once we've successfully registered this exception handler, we'll create a fake divide by 0 exception, and once this exception is thrown, all the registered exception handlers will be called, and these registered exception handlers can either return exception continue execution, which means that they've successfully dealt with the exception, or they can specify exception continue search, which means it's going to continue going through the next exception handler, traversing through the linked list and looking for a handler which can successfully handle the exception. If no handlers can handle the exception, well, then the program may crash. If it can't be can't be restored in any other way. So when we create this divide by 0 exception, it of course triggers our exception handler, and going through to our exception handler, we can check if the exception code matches what we're expecting, or the exceptions which we can handle. So that exceptions we can handle are divided by 0, as well. Of course, this is a very artificial situation. So what we'll do is we'll print the address of the context, where the RIP, the instruction pointer. So we'll print that out as almost a debugging, and then we'll increment the instruction pointer by 2 as to avoid an infinite loop where we keep causing this exception over and over again. Because bear in mind, the instruction pointer is currently where the instruction which caused the exception, and not incrementing it will cause it to throw the exception over and over again. So once we've incremented it, we can then tell the thing which invoked us that, look, it's all good, we've handled exception, you can now continue execution, and then it'll go ahead and print that it's recovered. If we look in the bottom right, this scenario which I've described to you occurs, where it prints the address of the instruction pointer where the exception occurred, and then it'll print the recovered statement. So when I was looking into kind of this, so this was essentially, this entire technique was in a blog post by Proofpoint, where they took a Nighthawk sample and reverse engineered it, and they kind of gave a couple of details out. Not too much, but just enough to tell me that, look, this is possible. And once I knew it's possible, I kind of knew where to look. And where did I start looking? Well, on YouTube, on GitHub, sorry about that. On GitHub, you've got the Windows XP source code, which was leaked a bunch of years ago. And looking at this source code, we can kind of get an idea for how exception handlers are added. So this is just the code ripped directly from the link in the bottom left, so for the exception handling stuff. And it's kind of described what I mentioned earlier. So if the first parameter, so the first handler is set, it will insert at the head, else it will insert at the tail. And of course, it's got to use a critical section as a synchronization primitive, because multiple threads can call this function, and we don't want to corrupt this doubly linked list. And in the bottom right, we've got this structure, which is kind of how it's stored internally back when Windows XP was around, which is, I think it's kind of different to how it's now done. Well, I can't honestly remember, but yeah, we'll see how we implement it later on. So our task now is to remove vectored exception handlers. And as we've seen earlier, our vectored exception handler works by, nowadays it works by encoding the function pointer of the exception handler in our linked list. And we won't see that until later on when we go about restoring it. But it will insert to either the head or the tail, depending on the value of the first parameter, also named first. So our goal, as previously shown here, is that we've got the where the list is implemented, which is RTLP callout entry list. But since we don't have access to private symbols, we need another way to obtain the head of this linked list. And once we've obtained the head of this linked list, there are multiple ways in which we can remove all the registered vectored exception handlers. And I must make this clear, this is only one way of doing it. There are many other better ways. So next we traverse the linked list, we can save all the entries, and then we can call remove vectored exception handler against all these entries. So the first steps first, so we want to first find the head of this linked list. So what we can do is we can add a vectored exception handler, is that we know that this is a linked list, and so we just create we add a dummy exception handler, and then this returns a pointer, and this pointer is actually just part of the structure, so we can cast it, and the first parameter of the structure is a plist entry, which is just a linked list entry, and then so we can just cast it, and then we can iterate through this this linked list, and we can compare it and see if the one of these entries are in the .data section. So the head of this linked list will be located in the .data section for NTDLL. So when we find a linked list entry that's within .ntdll, it is very, very likely, and it's almost guaranteed, that it's the head of the list that we're looking for. So once we do that, we can go through, we can traverse it. Get NTLDL section VA is just, of course, it's what the name suggests. And once we've traversed through this linked list, we can, and if we have found it, we can just break out of it. We can return the address of this the head, or we can just return null pointer. And of course, we've got to remove this dummy handler as we have no use for it. So once we've found that, we can then iterate through this. We will go ahead and save all these entries. The reason why we want to save these entries is that we want to remove vector exception handler. Of course, there are other ways to remove them. But yeah, so we've got an array, and this array is called VH handles, and it's of size 64. And we can store up to 64 exception handlers in there. If they're more than that, well, oh well, that's probably a weird program to have over 64 exception handlers registered. And once we've done that, we call remove vector exception handler against this, and this will, of course, call the internal functions and do most of the hard work for us. And that's still how we can clear it. The reason why we're saving it is, as we'll see here, is that if we want to restore it once we've done our nefarious activities, is that we can just call add vector exception handler again. But what we have to do here is that we have to call decode pointer on the vector handler, which is a function address, because internally vector handler, when it's add vector exception handler is called, it will encode the pointer for the function pointer as to not be overwritten by any exploit or something. But since we don't really care about that, it's mainly for us a completely different topic. But yeah, since it's an R process, we can easily just call decode pointer against its vector handler and re-register it and restore everything. You're free to try out this code. It's all available on GitHub, in my GitHub repository, one of them. I think it's the miscellaneous one. So now we've kind of gone through vector exception handling and how to remove these vector exception handlers and restore them. Another thing that was quite interesting in this Proofpoint blog post that Nighthawk did was use land DLL notifications, and that was kind of the next thing I looked to re-implement. So DLL load notifications and unload is we'll go through now. So what exactly are them? Taking the Microsoft definition for them, the registers for a notification when a DLL is first loaded and unloaded. And so the notification is a callback to a function we define with some information. So if we look at the bottom, load the DLL notification, the second parameter is a pointer to DLL notification data, and this DLL notification data is a structure we have to define. And within this structure, there's a bunch of information, such as the DLL name, where the DLL was loaded in at, and the size of the DLL. If you want to read more information about this, go ahead and check out MSDN, and this will contain a lot more information. The third parameter is just a context parameter, and I believe the first one is the notification reason. So in the way of what we did previously with vector exception handlers, we want to first actually kind of understand how this actually functions and how to use this in real behavior or real activity. A terrible thing is that load the register DLL notification is not exported by NTDLL. Actually, no, it is exported. We just have to call get proc address against it to get the exported address routine, and then we can call it. So this import API function is just a simple little macro which does some typecasting and type definitions. Thank you to Jonas for showing me and introducing me to macros and the cool magicness of macros. Of course, this code is all available. I can show it around. I can post links later for it. So we then call load a register DLL notification, and we'll point it to our callback. We also have to save this cookie in the p void. This cookie is actually a structure, and this structure is a linked list with some other parameters, which we'll go through in the next slide. And to kind of see this behavior, we'll call load library against debug help, and then we'll also call free library to see our DLL load callback routine called. So we've got this notification reason, and if our DLL is being loaded, we want to print the DLL load name. Else, if it's being unloaded, we'll just print that it's being unloaded. So calling this free library load library against debug help, we get this output. So all of these DLLs are loaded and then unloaded, and these are some other random DLLs which are loaded. So we kind of get an idea that when we register this DLL notification, it gets notified whenever DLLs are loaded and unloaded with a bunch of information that's here. So like the DLL base, the size of the image, and the full DLL name. What I've seen some EDRs do is register this function, so kind of they'll register that this loader register DLL notification function. And our goal now is to remove these notifications. In the same way we did with the vectored exception handler stuff, we're going to register a fake notification. And since it's implemented internally as a linked list, as we can remember from the cookie, which is we want to be able to find the head, which is again in the .data section of NTDLL, and then we want to unlink all the entries, and then optional, which isn't shown in this code, is relink all the entries. Of course, the way that I unlinked all the entries is just one way. There are, of course, many different ways of doing it. And the first thing we want to do is get the pointer to, well, the head in .data section for so we can unlink it as seen here. So the first thing we do is we register our dummy callback, as we said we're going to do it here. Once we've registered our dummy callback, we can cast it to a plist entry. As I mentioned before, internally this cookie is defined as a structure, and the first entry is a list entry. So we can just cast it to list entry and iterate it through this. So we can again call the same function we defined earlier, get NTDL section VA, and we can iterate through this linked list. And if any of these entries are within the virtual address space of the .data section, well, then we will unregister the DLL notification, because we don't want this dummy DLL notification to linger, and then we'll return the address of the .data entry. And if this doesn't work, we'll just return null pointer. So as we mentioned before, we get the address of the head, which is in the .data section of NTDLL, and now our next goal is to unlink all the entries. This is super simple, as it's just some basic linked list stuff. If you don't understand linked lists, I recommend you just pick up an algorithms textbook or go leak code. Or it's not that complicated. I can imagine a diagram would help for those not experienced with linked lists, but unfortunately I did not think of that. And yeah, it's really as simple as that. Once we've removed all these DLL load notifications, when we load the DLL, these notifications won't be called, and because they've been removed. And next thing we want to dive into is work items. Work items are a pretty cool thing, and kind of the main reason that people use these work items. So if you've got shellcode and you want to do something like load a HTTP library, an EDR might find this suspicious because if they do a call stack from an image load routine in the kernel, they'll see that this image load routine is, this load library is coming from unbacked read executable memory, in quotation marks. And again, credit to Nighthawk. Peter Winsmith is an absolute wizard. He's the guy who probably first came up with this. It's probably done before, but it's never been documented before or done for this purpose. And this is kind of an alternative to call stack spoofing. Call stack spoofing, I highly recommend checking out Claire's Virus's Silent Moonwalk. Again, shout out to Namazo for explaining a lot of the stuff behind call stack spoofing to a lot of us red teamers. And so yeah, big shout out to him there. And if we look below, what I mentioned earlier, so if we can use a work item, so work items are essentially just a thread pool, and we can queue these work items to this thread pool. And within this thread pool, these threads have a clean call stack, as they're a thread pool that everything implemented them. It was within like kernel 32 and NTDLL. And when we queue this work to them, so load library it'll have a completely clean call stack, as opposed to calling load library from shellcode, which would have not a clean call stack. So in this example, we can see by reading the parameter RCX, which is the first parameter of the argument in the x64 calling convention. So it's RCX, RDX, R8, R9. The first parameter is RCX. We can dump the Unicode, and we can see debug help, which is the DLL we try load, which we'll see in the next slide. So this is just a little wrapper around these work items. So there are two primary functions we can use for work items. There are a lot more, definitely. Just haven't discovered them yet. And so we can use RTL work item and RTL register wait. The main two things is that we can control the function address, well, the work, where the work is going to be executed, and we can pass a context to this, and this context is passed as the first parameter. So load library's function definition or type definition is that the first parameter it gets for W1, of course, is a string, and this string is like the DLL name. So since we can control all of this, we can submit this work item to this thread pool, and this thread pool will execute load library W on behalf of us and load this library for us. And we can either use RTL work item or RTL register wait. And simply this function, depending on the value of the Boolean switch, it'll choose either one of them, and then it'll return the address of the library. So previously we can just call, for example, we can call qload library with debug help.dll and 1 or 0, and it will execute one of these. The next slide is just an example. Do not do this in production malware. I don't know what production malware is, but if you're doing this on your red team engagements, this is not a red team tip. So one of the limitations before is that, as we can see, we can only submit one parameter to load library W. One way to get around this is by using nt-continue and setting up almost all the arguments in the registers, decrementing the stack pointer. So as I mentioned before, the calling convention on x64 is RCX, RDX, R8, R9. So we can move all these arguments. So we can write a wrapper almost around this. So first arg goes into RCX, second arg, RDX, third arg, R8, fourth arg, R9. So, and we also decrement the stack pointer by 8, and we set the RIP, so the instruction pointer, to the function address. So why would we do this? You've got ETW-TI, which is ETW threat intelligence, and some this ETW captures call stack trace. Some EDRs might look at this call stack trace, for example, if you allocate memory from unbacked memory or something. Yeah, it was just an idea. I'm pretty sure Elastic can detect most of these work items. I'm just telling you in lieu. So shout out to Elastic. They've probably got, for such a small security team, they're definitely doing like some of the biggest innovations. So shout out to them there. But yeah, this is just a simple wrap around get thread context. And since there is an ETW-TI event for setting the thread context, yeah, so we just use nt-continue. We set our context thread up. We call work item wrapper, and that should work. And as we can see, yeah, that's worked amazingly. And if we look at RCX, which is our first parameter, we can see it's the first argument, which in this case is get current thread, and we can see that's all been translated nicely. So let's move on to a couple compile time tricks. And what exactly do I mean by that? So I'm sure all of you know what entropy is. Entropy is really just a measure of randomness. There's different, there's many different definitions for entropy depending on what field we're in. And the way people have been fixing or lowering entropy is some ways is like concatenating Windows system DLLs. So they'll just literally just add their like kernel 32 DLL to the end of their binary and call it a day, and that might reduce the entropy, but that's not really a great way of doing it. Or another ways that I've heard people do, which is concatenating like the first chapter of Harry Potter and the Philosopher's Stone. Like, there are many ways people have, or unghastly ways people have doing it. And my approach to doing this at compile time, because I'm lazy, I don't want to do this once the binary's been compiled already is we'll define an array. We'll populate this array with the same character, and then we'll store it in either the .type section or the .data section. So why would we do this? So when we have our shellcode and we're storing it in .text section or the .data section, this will raise the entropy of this section, and we can just counteract this by creating an array with the same character and lowering the entropy. And the reason why we do this stuff in main is that we don't want this code to be optimized out by the compiler. And this actually does work. It's not great, but it does work. As I'll show you the before and after. So before, we've just got basic int main function, or just a basic empty program. It's 11 kilobytes, an entropy of 4. The .text section quite small, 3.5 kilobytes, and the .text section 512 kilobytes, which is like default. And then once we have done this fake array and stored in the .text section and .data section, it goes up to 137 kilobytes. The entropy is 1. So a bit more on like what entropies are suspicious or not. So when you've got a packed binary, your entropy is typically a lot higher. It's not like 6 to 7. That's or 7. Can't remember, to be honest. But yeah, packed binaries are because they're more random, because it's encrypted. The entropy is a lot higher. So by lowering the entropy to almost as 1, which is almost suspicious, on the other hand, like almost as suspicious as a high entropy. But yeah, this is just really a demonstration purpose. We know that the entropy has been reduced because, well, we've got almost 120 kilobytes of empty characters, which is awesome. It's awesome. And another cool trick is that a lot of people do like compile time API hash. Don't do compile time API hashing, and they go ahead, write a Python script. They submit each of these strings individually, and then they submit it to the string. It compiles, and then they get back this hash, and then they store it in a header file. And then if they have to change the hashing algorithm, they've got to do it all again for all of those strings. So a simple way is a nice feature of C++ is that you can is compile time evaluation. So we can hash strings at compile time, and the main benefit of this is if we want to change the hashing algorithm or the main prime hashing number, so 5381 in this example, we can do it pretty easily by just changing hash string DGB2 to point to a different hashing algorithm. And most of these hashing algorithms, like if you just go to the VX API repository, you've got a couple there. You probably have to just change a couple things to make them make the compiler happy. So for example, unsigned char C, if we don't set that to 0 and we just leave it as C, the compiler will complain because it needs to know what C is at compile time. And yeah, we can show that this works by doing a static assert and showing that this has been able to evaluate at compile time. So yeah, it's pretty easy. What's really cool is that you can really mess with things like HashDB by doing random hashing functions and incrementing like there's a whole other realm of stuff, but yeah, you can really mess with some of these systems which look at pre-compiled hashes. So I think Sentinel-1 okay, maybe not Sentinel-1, but some EDRs will block when you have certain known API hashes, like the ones in CobbleStrike. So moving on to like almost the most boring topic of the day is hardware breakpoints. It's not so much as random, but there hasn't really been much stuff for malware that leverages our hardware breakpoints, which is kind of the main reason I did like this small little paper for VX Underground in their Black Mass Volume 1. So if you're interested, be sure to check it out. A lot of other cool papers in there, some stuff on mini filters, some really cool stuff on antivirus as well. So yeah, go check that out. All this associated code is in the GitHub repository mentioned in the bottom right. So our task is kind of to trivially hook functions, and we want to divert the code flow as we want. And what we don't want to do is have to patch the memory with like jumps or other ways in the memory. Yeah, so we don't really want to do in-memory patches. And kind of what you really need to know for the rest of this is each thread has its own context, and this context is essentially just a snapshot of all of these registers. So we've got these debug registers, and 0 through 3 specify the addresses, and 7 specifies the conditions, and like the preliminary conditions to actually trigger on those specific addresses and throw an exception. So we previously discussed about vectored exception handlers, and we can register a vectored exception handler to capture these debug register exceptions, and we can remove and set these debug registers with syscalls, because it's a privilege to do this. Is a privileged thing. So to set hardware breakpoints, really all we do is we've got our context. We specify in the context flags we want to set the context debug registers. We get the thread context. We set the debug register. So what you're seeing with the DR0 and then typecasting it, well, indexing it with the pos, is so we avoid having to do a switch. What I see a lot of other implementations for hardware breakpoint do is that they'll do like switch pos and then do context.dr0, context.dr01, context.dr02, and it's just like 8 lines of code which you can be done in like 1 line of code, which is I don't know why they don't do it. Yeah, that's it. That's very simple. And then once we do that, we set the thread context again, and easy and simple. So as far as like hooking AMSI or EDW goes, this is essentially using the library or all the code mentioned in this repository in the bottom right. And what we can do is insert descriptor entry, which is essentially just like the API for this library. And we set it to the address of, for example, AMSI scan buffer. And we point it towards riprep patch, which is just a simple function which will get called by the exception handler, as we'll see later on. And what this does is it will set the instruction pointer when AMSI scan buffer is hit to the address of the next ret instruction. We do this by finding the gadget for the opcode C3, which is the return instruction, and that's pretty simple, just doing like a simple memory comparison and incrementing and going on and on. And once that's done, we set the resume flag so we can continue execution. So how exactly does this relate? This riprep patch get translated and executed. So we've got our exception handler, which is obviously the stuff we register with the exception handler. We'll add that to the exception handler. And when it's a single step exception, which is what debug registers throw, we maintain internally a linked list. And this linked list has entries added and removed by insert descriptor entry. And if all the conditions matches, so the address matches the current instruction pointer and the thread ID matches the current thread ID, then we'll execute temp.fun exception info. We'll call that, and then this will execute. In the case of AMSI scan buffer, it'll go ahead and call the riprep patch. And then it'll mark resolved as true. And then because resolved, it has been resolved, we'll say that we can continue execution and we don't want to continue searching. So some other examples is, for example, say we want to hook heap 3, and we're operating like in Cobalt Strike, and we want to hook the heap 3 so we can clear all the memory. And if there's any confidential information, we don't want our process to be dumped. We don't want an EDR or an AV to scan our process and see these certain bytes. We want to mem set all the heap 3s, because when something is heap 3'd, it's not guaranteed to be zeroed out. So what we can do is we can insert a breakpoint on the address of heap 3. We can then get the size of the heap that's being freed, because this isn't a parameter to heap 3. Using the parameters passed to heap 3, we can pass the heap size to get the size. And then we can mem set it. And once we've mem set it, we can say we can continue. So the R rate is the address of the memory. So if you look at the third parameter of heap 3, which is memory, that's the memory that we've allocated. So we can just mem set that information. And yeah, it's simple like that. This hardware breakpoint engine that I wrote is pretty easy to use. I recommend having a play. It's super easy to add your own hooks and focus more on what the hook does instead of how to do the hook. So with all that, I know it's been very quick. I've spoken very fast, and I'd like to open up the stage to Q&A. I may have answers to your questions. I may not have answers to your questions, and of course, the slides will be available. Are there any questions?